And good morning, everyone. Welcome back to a new chapter, a new section, a new day. Today, we're going to be talking about series and sequences. But before we get into that, I want you to go through your warm-up. So think about how the balls are set up before the break on a pool table. If you look at any of the corners, there's a single ball. And then if you move down or away from that corner, it goes to 2 balls, then to 3 balls, etc., etc. So the first question is, how many balls are in the triangle before the pool game? Now, create a 2-column chart. And in the first column on the first row, it's going to be row 1, row 2 is going to be row 2, row 3 is row 3, etc., etc. Then in the second column, write the number of balls in each row. So how many balls are in row 1? Then how many balls are in row 2? What do you notice about the relationship between each row? How do you get from row 1 to row 2, and then row 2 to row 3? And then if there was to be a 6th row of balls, how many balls would be in that row? And then how many balls would be in the triangle in total, assuming you can make the triangle a little bit bigger? And how do you know how many balls are going to be in that row and how many balls are going to be in the triangle? And I want you to think about this. Okay, like we said earlier, we're going to be going to chapter 8.1, defining and using sequences and series. So last week, you were solving rational equations by cross multiplication, using function inverses and the least common denominator. And this week, we're going to go off that path a little bit, and we're going to use sequence notation to write terms of a sequence, including the nth term, and sum the terms of the sequence to obtain a series with summation notation. So when we're talking about sequence notation, looking at that triangle from the warm-up, we know how many balls are in row 1, 2, 3, 4, and 5. There's obviously a pattern, so we could write a function to determine how many balls will be in the 8th row, or the 11th row, or the nth row. Some new vocabulary we're going to be working through in this section. We're going to be using the word sequence, terms, series, and summation notation. And when you take a minute and pause the video, if you thought of or heard any of these before, write down what you think they mean. We're going to go through a more formal definition later, but just think about it for a moment. And here we have our first definition. A sequence is an ordered list of numbers. A finite sequence is a function that has a limited number of terms whose domain is the finite set 1, 2, 3, all the way up to n. And the values in the range are called the terms of the sequence. So if you think back to our pool balls in the warm-up, the domain would have been the first row, the second row, the third row, the fourth row. And then the range would have been the numbers 1, then the numbers 2, then the number 3, number 4, because that's the number of balls that correspond to those rows. An infinite sequence is a function that continues without stopping and whose domain is a set of positive integers. Here are examples of a finite sequence and an infinite sequence. So a finite sequence might be the terms 2, 4, 6, 8, but an infinite sequence would be the terms 2, 4, 6, 8, or all even integers. A sequence can be specified by an equation or a rule. For example, both sequences above can be described by the rule a sub n equals 2n, or f of n equals 2n. So example 1a is to write the first 6 terms of the sequence, the quantity -3 raised to the n minus 1 power. And when you're trying to write the terms of a sequence, you want to start off and you want to make a list. You have a sub 1, a sub 2, a sub 3. believe that's there. Yes. And then when you do this, all you want to do is you want to substitute the term number in for the variable to get the term. So we're starting on the last page with a sub n equals a rule. So where we have a sub 1, we just substitute 1 in for n. And we get the quantity -3 raised to the 1 minus 1 equals -3, the quantity -3 to the 0 power, which just equals 1. And then repeat down the line. So a sub 2 equals the quantity -3 raised to the 2 minus 1 equals -3 to the first power equals -3. So go ahead and complete the answers. What do you get for a sub 3, a sub 4, a sub 5, and a sub 6? So the first 6 terms of the sequence of the quantity -3 raised to the n minus 1 are 1, -3, 9, -27, 81, and -243. So for example 1b, it wants you to write the first 6 terms of the sequence 2n plus 5. So remember, the first thing you want to do is you want to set up your chart and then write the first 6 terms of the sequence 2n plus 5. So for example 2a, you are to describe the pattern, write the next term, and write a rule for the nth term of the sequence. So the sequence we have here is -1, -8, -27, and -64. So we're looking for a rule or a pattern that connects these numbers together. So they don't increase linearly, so addition and multiplication won't work. It's not like the pool balls where you're adding 1 to each row, or the even numbers where you add 2 to get to the next term. These aren't the squares of integers, but they are the cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Since the signs are negative, and we're raising an integer to a cubic power, we keep the sign, so the pattern must be the quantity -n to the third power, or the quantity -n cubed. So then we test this. We try it on our first term, and we get the correct answer. The second term, the third term, and the fourth term all correspond. So applying this rule, what do you get for the 5th term of the sequence? And you should get the 5th term is a to the 5th equals -125. So then our rule is a sub n equals the quantity -n raised to the third power. So for example 2b, you're asked to describe the pattern, write the next term, and write a rule for the nth term of the sequence. So just looking at the sequence that we have here, we have 0, 2, 6, and 12. So how do you get from 0 to 2? You add 2. And then think, how do you get from 2 to 6? And then how do you get from 6 to 12? So going on that pattern, what do you think the 5th term of the sequence is going to be? All right, and now we have to write a rule for the sequence. So if we look at the term, we saw that we add 2, then add 4, then add 6. So judging by this, the next number should require adding 8. So to get the first term of the sequence, we're starting at n equals 1. It makes sense to subtract 1 because the easiest way to get from 1 to 0 is subtract 1. So we're going to guess that the pattern is going to be a sub n equals n minus 1, because that works for a sub 1. So a sub 1 equals 1 minus 1, which equals 0. However, when we try this for the second term, we can't use n minus 1 because a sub 2 would equal 2 minus 1, which equals 1, and 1 does not equal 2, which is the second term of our sequence. So we need something a little bit more. Well, if we build on the original idea, we can use n minus 1 times n, or n minus 1 plus 1. So go ahead and test this out. Which of these rules applies for the first and second terms of the sequence? So if you test this out they both work for the second term of the sequence, because 2 minus 1 equals 1 times 2 is 2, and 2 minus 1 equals 1 plus 1 also equals 2. But when you apply this to the first term, the a sub 0 or a sub 1, you get 1 minus 1 equals 1 plus 1, but 1 does not equal 0. But 1 minus 1 times 1 equals 0, and that equals 0. So it looks like the correct pattern we want to use is n sub 1, n minus 1 times n. The quantity n minus 1 times n, I'm sorry. So go ahead and test this out for the third and the fourth terms of the sequence, and then use that to determine what is the fifth term of the sequence. So we get that the solution is a sub n equals the quantity n minus 1 times n, and our next term in the sequence is going to be 20. All right, so example 3a asks you if a table in a grocery store stacks apples in the shape of a square pyramid with 7 layers. And it wants you to write a rule for the number of apples in each layer. And then what would be the number of apples if the store expanded the pyramid to the 14th layer? So take a look at the picture on the right. There's 1 apple in the first row, and then there's 1 apple on each corner in the second row. So there's 4 apples in that row. And you can see the third row is 3 apples by 3 apples. So you know there's 9 apples in that row. So what's a rule to find the number of apples in each layer? So by applying that logic, you should get that the rule to find the apples in each layer is a sub n equals n squared. So if this store were to expand the apples to the 14th layer, how many apples would be in the 14th layer? So you substitute 14 in, you get a sub 14 equals 14 squared, or there would be 196 apples in the 14th layer. So for any of you who work in a grocery store and work in produce, this is a great test, and see if your store would approve of it. Strongly suggest you don't try it, though. It's very hard to keep balanced. All right, our next major concept deals with series and summation notation. So when the terms of a sequence are added together, the resulting expression is a series. A series can be finite or infinite. So thinking back to the even integers from before, a finite series would be 2 plus 4 plus 6 plus 8. And an infinite series would be 2 plus 4 plus 6 plus 8 plus ... meaning that it goes on forever. And you can use summation notation to write a series. So for example, the 2 series above can be written in summation notation as follows. A finite series, so 2 plus 4 plus 6 plus 8, equals the sum of 2i for the values of I equals 1 to 4. And the infinite series can be written as the sum from I equals 1 to infinity of 2i. So the lower limit is on the bottom, and that's where you're starting. That's the first term in your sequence, so a sub 1. And the number above the sigma is your limit. So for a finite series, it's going to be 4. If it's an infinite series, it's going to be infinity. And summation notation is also called sigma notation because it uses the uppercase Greek letter sigma, written as that funky E there. And when written in summation notation, the finite series is read as the sum of f of x for values from a to b. So for the finite series above, it'd be read as the sum of the values of 2i for the values of I from 1 to 4. I generally say the sum from I equals 1 to 4 of 2i. So if you hear me refer to that way, that's just the way I do it. All right, for example, 4a, you are to write the following series using summation notation. 1/2 plus 2/3 plus 3/4 plus 4/5 plus ... So if we're looking at this, if we're starting at a sub 1, and we look at the numerators of each fraction, we go from 1 to 2 to 3 to 4. So our numerator is going to be n. If we let 1/2 be the first term, a sub 1 equals 1/2. And if we look at the denominator, we're going from 2 to 3 to 4 to 5. So if we're starting at a sub 1, then it looks like the denominator is going to be n plus 1. And that holds true. So we have n over n plus 1 is 1 over 2. N over n plus 1 is 2 over 3, etc. So a sub n equals n over the quantity n plus 1. And testing this for each value in the series confirms our hypothesis. And since the series goes on forever, given by the 3 dots at the end of the example, so we have 4 over 5 plus ... We know it's going to be an infinite series. So we're going from I equals 1 to infinity. And then the summation notation is as follows. The sum from I equals 1 to infinity of I over the quantity I plus 1. You can do the sum of n equals 1 to infinity of n over the quantity n plus 1. As long as your variable is consistent, it doesn't matter. And the reason that the infinity and the I equals 1 are not in the top and bottom respectively is just limitations with technology and equation editor. All right, so example 4b is to write the following series using summation notation. 25, 50, or 25 plus 50 plus 75 plus ... plus 250. So think about how you're getting from 25 to 50, from 50 to 75, 75 to the next term. So the first question is, what do you think is the function that relates each term in the series? So you should get a sub n equals 25n. And then what is the maximum limit of the series? So what's the top number on the sigma? So then which of the following would be the correct notation for this series using summation notation? All right, and for example 5, you are to find the sum of the series from k equals 4 to 8 of 3 plus k squared. So if you look at the sigma, we're starting at k equals 4 and just going up to k equals 8. So right now, we don't have any tools or shortcuts to solve something like this. So all you want to do is you want to substitute in each value from 4 to 8 inclusive into k and add it together. So you get 3 plus 4 squared plus the quantity 3 plus 5 squared plus the quantity 3 plus 6 squared plus the quantity of 3 plus 7 squared plus the quantity of 3 plus 8 squared. So when you plug that into your calculator and solve it, what do you get for the sum of this series? And you should get the sum of the series is 205. All right, and these are formulas for special series. So if we're trying to find the sum of n terms of 1, so from the sum of I equals 1 to n of 1, it's just going to equal n. So if we're going from I equals 1 to 10, and we're adding 1 10 times, we're just going to get 10. So the sum of the first n positive integers, so the sum from I equals 1 to n of I, you can do this without adding up of n times the quantity n plus 1 all over 2. And if we're looking for a sum of squares of the first n positive integers, so from the sum of I equals 1 to n of I squared, you can solve it easier by doing the formula n times the quantity n plus 1 times the quantity 2n plus 1 all over 6. And that's just a shortcut so you don't have to do like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. It's okay if n is a smaller number, but if you're going from n equals to say 25 or 26, it can get a little tedious. So this formula is a great way to solve it a little bit quicker. All right, and for example 6, the table in the grocery store stacks apples in the shape of a square pyramid with 7 layers. How many apples are in the stack? This is the exact same problem as in example 3. So think back to how we had the square pyramid. In the first layer there was 1, in the second layer there's 2, in the third layer there's 3. And refer back to the chart on the previous page. How many apples are going to be in the stack given that we're using the series n squared? And if you look, so we'll get the series from I equals 1 to 7 of I squared equals n times the quantity n plus 1 times the quantity 2n plus 1 all over 6, because that's our shortcut for finding the first terms of a square series. Substitute in our values, get 7 times 8 times 15 over 6, and there should be 140 apples in that stack. So in closure, think again about the pool balls in the triangle from the beginning of the class. So I want you to write a series using summation notation to determine the number of the balls of the triangle. And then can you use any of the 3 shortcuts to solve this series? So can you use the I equals 1 to n of 1, I equals 1 to n of I, or I equals 1 to n of I squared? And then if you can use a shortcut to determine the number of balls in the triangle, does it hold up if you had a 6th row of balls? And if it cannot, explain why you can't use this shortcut. So make sure you check Google Classroom, make sure you don't have any homework. I want you to finish this up. And tomorrow we'll be doing some practice problems as a class together. I hope you all have a wonderful day, and we'll see you all tomorrow.